All right, so picking up where we left off in this problem, we were saying that in order to find the variable matrix x, again, which is going to tell us the values for x1, y, or x1, x2, excuse me, in order to get there, in order to pull that off, looks like the next phase is going to be calculating and understanding what A inverse is going to be equivalent to. Because we already know matrix B, again, that column matrix of 8, 1, we already know that. And then once we know A inverse, again, it's just merely a multiplication problem. So in calculating the inverse of A, we do have options. Option number 1 would be to write out matrix A like this. We could augment this with the identity 1, 0, 0, 1. If you're following the directions to a T, this is kind of what they're telling us to do. And we could use the elementary row operations to essentially make the left side into reduced row echelon form, which is going to give us values on the right side that will be A inverse. Okay. So again, we all know and remember, I hope, this process. Again, calculating, finding the inverse. Again, this is something that if this were a 3x3, you would have to do it this way. By the way, hint, hint, be ready to do that on Monday's test. But for this problem, luckily, since it's a 2x2, we have another option. We can actually figure out the inverse by, again, if we had just a generic matrix A, again, we have this little formula. If A is in this format of A, B, C, D, we can say that A inverse is going to be 1 over the determinant of A times, we've got to jumble this up slightly to where D and A swap places, B and C become their opposites. So this, again, is our formula that we can use to calculate and solve for A. So if we were to use this formula, again, I want to be able to see matrix A on the same slide. This is saying that A inverse is going to be equivalent to, again, we are using A right up here. This is what we're looking at when we're talking about matrix A. So we've got to calculate 1 over the determinant. So the determinant of a 2x2 matrix, remember we're multiplying the diagonal. So if I were to multiply diagonally going down minus the diagonals, going up. Multiplying diagonally going down 2 times negative 8 is negative 16. Multiplying going up 3 times negative 5 is negative 15. And then we have to jumble the order. So again, top left, bottom right, they're going to swap places, which means negative 8 comes here, positive 2 goes there. Top right, bottom left, they're going to be negated. So negative 5 becomes positive 5, 3 becomes negative 3. So now what we have going for us, again, is the ability to say that A inverse is going to be equivalent to 1 over, now since I'm subtracting negatives, that's adding the opposite. So we're going to say that that scalar is going to become 1 over negative 1, which I think that we're all on the same page. If I have 1 over negative 1, that really just means the scalar is going to be negative 1, which simply means that for my inverse, we're essentially negating all 4 terms. So that's going to put us at positive 8, negative 5, positive 3, negative 2. So again, this is not my answer. Remember what we stated previously was that we're trying to solve for x. And we know now that A inverse times B is going to give us that value for x. So again, x is equal to A inverse, which is 8, negative 5, 3, negative 2, times B, which we're going to scroll back to the beginning of this problem because it's been a while since we've looked at B. Remember what B is equivalent to. It's a column matrix 8, 1. So times the column matrix 8, 1. This should help us to figure out what matrix X is equivalent to. So off to the side, it's probably going to be wise for us to test to see if we can even do this. So matrix A inverse is a 2x2 matrix. Matrix B is a 2x1 matrix. We're noticing that the middles match. That's great. We're also noticing that our solution is going to be another 2x1. So now we know that X is equal to, we're searching for a 2x1. So 2 rows, 1 column. All right, so multiplying first row times the only column. 8 times 8 is 64. 5 times negative 1 is negative 5. Second row, only column. 3 times 8, 24. Negative 2 times 1 is negative 2. So this is going to lead to X being, we'll call it 59, and 24 minus 2 is going to be 22. So if you were asked on the test, what is matrix X? this is it. We found it. There is matrix X. But if we were to ask you to go a little bit further and to identify specifically, well, what is X1? We'd say, well, that's 59. And what is X2? That's 22. Most commonly, we're going to put this as an ordered pair, which would be 59, 2, or a final answer. So that's what we're talking about in problem number 5. Problem number 6, here we want to find the inverse and we want to find the determinant. I'm going to be honest with you, it's probably going to be smart for us to do that in the reverse order. I think it's going to be easier for us to find the determinant first. Again, as we said previously on the other slide, we could find the inverse by doing this, 6, -4, -2, 1, and augmenting with the identity. In fact, you know what? Let's do it that way. So again, this way we're getting some more practice with the elementary row operation. So the first thing I think we might want to do here, this seems kind of like an odd step, but let's actually swap rows 1 and 2. So if we were to switch these, it's going to be -2, 1, 0, 1, and 6, -4, 1, 0. So from here, excuse me, from here, after we've swapped these rows, now what if I were to say, let's see here, let's say this without just going right out and saying it. If I were to take 3 times the first row plus the second row, so 3 times row 1 plus row 2. Essentially what we're doing is we're targeting 6. Maybe I should have started with that, meaning that row 1 stays the exact same. For row 2, you're going to notice, if I were to triple the first row and add it to the second, that's going to give us a 0 here. Triple the first row and add it to the second, that's going to be 3 plus -4 is -1. Triple 0, still 0 plus 1 is 1. 3 times 1 is 3 plus 0. We're looking now at this. So hopefully you're starting to understand why we chose to do this. Basically, we're trying to stay away from fractions as long as we can, which means that we could target the row in column 1, that -2, but instead, again, you have options. You could go at the -1 first. You know what? I guess I'm kind of torn as to how we want to do this. I think it's going to be easiest, or best for us, I should say. Maybe not easiest, but best for us if we target row 1, column 2. So if I were to try to turn that 1 into a 0, I think we could get there with a very direct addition problem. Meaning, if I were to just simply say row 2 plus row 1, thinking about what that's going to do for us. Row 2 plus row 1, now we have -2, 0, 1, 4. And now, honestly, it doesn't really matter which order we go. Yeah, we're going to see a fraction in here, but we have to figure out a way to turn that -2 into a +1. So for the time being, we're going to leave the second row alone. But I need to turn that -2 into a +1, so I'm going to take -1/2 times the first row. So -1/2 times -2 is 1, -1/2 times 0 is 0, -1/2 times 1 is -1/2, and -1/2 times 4 is going to be -2. So last piece that we have here, row 2, column 2, that -1, it has to turn into, or it has to become a +1. So again, our top row is exactly as we want it. The bottom row, though, that -1 needs to become a +1, so I'm going to run a negative through the second row. So essentially negating everything. 0 stays 0, now +1, -1, -3. So my inverse, A inverse, is going to look exactly like this. So what is A inverse? It is -1/2, -2, -1, -3. Now, all throughout this process that we just completed, realizing, of course, that most of you probably did not do it that way. Again, most of you are probably going to choose to use the formula, which is totally fine. If we were to go back to this problem, we're also asked to find the determinant. So the determinant here, again, slightly different setup. We're going to say 6, -4, -2, 1. In a 2 by 2, we're going to say that the determinant is the sum of the downs minus the sum of the ups. So multiplying going down, 6 times 1 is 6. Multiplying going up, -2 times -4 is +8. And that tells us 6 minus 8 that our determinant is -2. So once we know the determinant, just so we can say we did it, if we were to look back at the original matrix A, if we wanted to find the inverse using 1 over the determinant, which we just found to be 2. So negative 1/2 times. We jumbled the order, that's going to switch from 1 and 6. That's going to negate. Negative 4 turns to 4, negative 2 turns to positive 2. And now that we have this scalar of negative 1/2, we could also say that, yeah, the inverse, if I scale it through, is going to be negative 1/2. Negative 1/2 times 4 is negative 2. Negative 1/2 times 2 is negative 1. Negative 1/2 times 6 is negative 3. And if we're looking at this inverse, boy, does that look familiar. It's the exact same. So it's going to be up to you as to which method you choose. Again, most people tend to pick the, I don't know why I can't think of the words I'm trying to use, but the formula. So in terms of what I'd like for you to do, kind of show me that you actually did this. What I would like for you to do is to build a matrix. Again, we will have you write PLHS, map, and clef. Got to get in on that. So you are going to build a 3x4 matrix, PLHS, map, clef. You'll put that in the top left corner. Again, not the right corner, but the top left corner. That's going to be my indication that you actually did this. So last problem that we have here, we want to solve the following system of equations using these matrices. We want, it goes on to say that you may use an augmented matrix equation, or Cramer's rule to solve the system. What that means, again, is if we made this an augmented matrix, we could do this a whole lot like we did the first problem, where we go into reduced row echelon form. If we did a matrix equation, we're going to solve using inverses. If we did Cramer's rule, that's going to be my assumption, anyway, as to the way that a lot of us would prefer to complete this problem. But if we did Cramer's rule, then we need to solve for x, solve for y, solve for z, and we go about it that way. So I'm going to do this using Cramer's rule, which means that I need to begin by writing up the matrix equation. So 2, 3, 1, 3, 3, 1, 2, 4, 1. This is my coefficient matrix times my variable matrix of x, y, z is equal to my constant matrix of negative 1, 1, negative 2. So first up, I need to figure out what the determinant d is equivalent to. So looking at my coefficient matrix of 2, 3, 1, 3, 3, 1, 2, 4, 1, the way we find the determinant, I've got to copy the first and second columns over. And now we're going to say, identify that the determinant is the sum of the downs minus the sum of the ups. So multiplying going down, 2 times 3 times 1 is 6. 3 times 1 times 2 is also 6. 1 times 3 times 4 is 12. 6 plus 6 plus 12 is going to be 24 for the sum of the downs. Now going up, 2 times 3 times 1 is 6. 4 times 1 times 2 is 8. 1 times 3 times 3 is 9. So now the sum of the ups, it appears to be, what's that, 23, it looks like. So the sum of the downs was 24 minus the sum of the ups, which was 23. So it appears that our determinant here, d, is equal to 1. Now, that's a big deal for us, of course, because we're going to use the determinant when we solve for dx and dy. But the big deal moving forward is that it's not 0. If we got 0, we would be in trouble. What we're going to try to play off is the fact that x is going to be equivalent to this value that we're about to find of dx divided by d. We're also going to say that y is equivalent to the value of dy divided by d. We also know that z is equivalent to the value of dz divided by d. And obviously, d, the determinant, right here, is going to show up in all three of those little basic formulas. So next up for us is to figure out dx. So dx, this is when we take the original coefficient matrix. Just go with me on this for a moment. Of 2, 3, 1, 3, 3, 1, and 2, 4, 1. And if I'm targeting the x, again, this is my x column, this is no longer going to be my x column. In its place, we are going to substitute in the constant matrix, which if we go back, the constant matrix was this one. So negative 1, 1, negative 2. So negative 1, 1, negative 2 is subbed in its place, and now we need to find the determinant. So finding the determinant is going to give us this value of dx. I'm about out of time, so I'm going to have to spill into a third part here. So uploading now.